Gosowich as an example. Let's pretend we're interested in estimating Tuffy's true strikeout probability using only the information that in 2015 he was a major league hitter who struck out 23 times in 138 plate appearances. Now the naive estimate of his strikeout rate would be 16.7%, but regression to the mean suggests that a better estimate would be 17.5%. Now where did we get this number 40 from as the number of league average plate appearances to add to Tuffy's results? Well, here's the equation where sigma squared t is the variance in true strikeout probability among major league hitters. Let's talk about where this equation comes from. We assume that the true strikeout rates of major league hitters follow a normal distribution with mean p bar and variance sigma squared. And for an individual hitter, given his true strikeout probability p, his observed strikeout rate p hat follows a normal distribution with mean p and variance sigma squared L, where sigma squared L can be interpreted as variation due to chance or luck. Now these two assumptions might not be exactly accurate, but they're close enough to the truth to give us a reasonable result. Now given our observation of the data p hat, our best guess of p is p star, the conditional expectation of p given p hat. What I want to point out here is that p star is the estimator which minimizes the conditional expectation of the squared difference between itself and the true strikeout rate p, conditioned on the data p hat that we've observed. This is going to be important later. Now in this case, p star is very easy to compute. It's just the weighted average of p bar and p hat weighted by the inverses of their respective variances, and that's regression to the mean. So today I'm going to introduce you to regularized linear regression, and I'm going to explain its relationship with regression to the mean and compare it with a linear mixed effects model, which is the basis of deserved run average like Jonathan was talking about this morning. The purpose of this talk is not to introduce a new batting statistic. We have plenty of those. The purpose is to explain the relationships between a few different estimators of true talent. After that, Eli is going to show you what happens when we actually apply these estimators to the 2015 Major League Baseball regular season data. So at this point, let's consider a different model for estimating the true strikeout rate for an individual. In this linear model, we'll say Ki is an indicator of whether the ith plate appearance results in a strikeout, and Bi is the identity of the batter in that plate appearance, for example, Paul Goldschmidt. In our model, we have a parameter alpha, which corresponds to the league average strikeout rate. And for each batter B, we have a parameter beta B, which corresponds to how much more likely than average that batter is to strike out. And our model says that Ki is equal to alpha plus beta Bi plus Gaussian noise. It's not a good model, but we'll get to that later. Now for each batter, our estimate of his true strikeout rate is alpha hat plus beta hat B. And if we fit alpha and beta in this model using the standard least squares criterion for linear regression, then our resulting estimate for each batter is just his total number of strikeouts divided by his total number of plate appearances. In other words, the result of this model is exactly equivalent to using observed strikeout rate to estimate the player's true strikeout probability. But let's take this a step further, and instead of minimizing the sum of squared errors in the linear regression, let's instead minimize the sum of squared errors plus lambda times the sum of squared beta coefficients. This is called regularization and encourages our betas to be closer to 0. Now, if we solve this optimization problem in the second equation, then the result is beta star B given in the third equation, where NB is the number of plate appearances for batter B. Beta hat B is our estimate of his beta in the linear regression in the previous slide. So what we see here is a weighted average of two different things, much like regression to the mean. So let's explore that relationship in more detail. In this slide, in the top half, I've rewritten our equation for regression to the mean. And in the bottom half, I've written our estimate of the true strikeout probability for an individual batter based on our regularized linear model on the previous slide. Now, using the fact that alpha hat is equal to the league average strikeout rate P bar, and alpha hat plus beta hat is equal to the observed strikeout rate P hat for an individual batter, we see that the result of fitting our previous model is that for every batter we predict as our estimate of his true strikeout probability, it is a weighted average of p bar and p hat. And so in fact, if lambda is equal to n sigma squared L divided by sigma squared T, then these two estimates are exactly equivalent. So what's important here is how do we choose sigma squared T for regression to the mean, and how do we choose lambda for regularized linear regression? Well, for regression to the mean, what we do is we compare the spread in our metric to the spread sigma squared L, which we would expect if all players had the same skill. Intuitively, the difference between these two is how we get at sigma squared T, and how we estimate it. You can look at Appendix A of the book by Tango, Lichtman, and Dolphin for detailed explanation of this. Now, for the regularized linear model, we choose lambda through a process called cross-validation. Now, I could spend more than 20 minutes explaining cross-validation, but the idea is that we're choosing lambda, which minimizes our prediction error when we use this model to predict true strikeout probabilities for individual batters. And so in that sense, we're doing something very similar to regression to the mean, where regression to the mean is minimizing the expected error between our prediction and the truth, conditional on the data that we've observed. And this right here is the difference between regression to the mean and the regularized linear model that I've introduced. It's just a matter of how we estimate the appropriate amount of shrinkage to do. So now that we've established the relationship between a regularized linear model and regression to the mean, let's get a little bit more sophisticated and consider a logistic regression model, which more appropriately models the indicators of strikeouts as being binary random variables with some probability of being equal to 1. We can fit this model much the same way as we did the previous one with a regularization on the beta coefficients. And that results in a reasonable model that gives us an estimate of the true strikeout probability for every batter. We're going to call this estimator the ridge estimator, the ridge regression estimator. But let's go ahead and move on to our proposal of true wOBA. So the data that we're going to use for true wOBA are for each plate appearance I. YI is the outcome, which can be one of ground out, fly out, strike out, walk, hit by pitch, single, double, triple, and home run. BI, PI, and SI are the batter, pitcher, and stadium, respectively, in the ith plate appearance. HI is an indicator of whether the batter is on the home team, and OI is an indicator of whether the batter and the pitcher have opposite handedness. And this is where we can really use the power of a regularized linear regression model to extend regression to the mean, because we can build a linear model which has coefficients for all of the data listed above, thus adjusting for all of these variables. And we can also model the response as being multinomial, meaning that if the probability of a strikeout increases, that means that there's less probability to go around for all of the other outcomes. Now, if we fit this model by minimizing the negative log likelihood plus regularization term on the coefficients, then what we're doing is we're estimating the skills of all of the batters in producing each of the outcomes while simultaneously adjusting for sample size, skill of the opposing pitcher, park effects, and then advantages due to a home field advantage and to a handedness platoon advantage. Now, once we fit this model, what we have is for every batter, an estimate of the probability that he produces each of the 9 different outcomes in a plate appearance against an average pitcher in an average stadium. We multiply each of these outcomes by the corresponding weights for wOBA, and that gives us our true wOBA. Now, the astute among you may have noticed that true wOBA is very similar to a simplified version of DRA for batters, DRA being deserved run average from Baseball Prospectus. So let's examine this relationship a little bit closer in the simple example of just trying to model the true probability of a strikeout. Here's a random effect model, which is the basic building block for the linear mixed effects models that Jonathan was talking about this morning. The difference is that instead of having a penalty on the beta coefficients, what we do is we put a mean 0 normal prior on the beta coefficients. This has a similar effect of shrinking them towards 0. And so the difference between the random effect model and the regularized logistic regression, which is the basis for true wOBA, is how the amount of shrinkage is determined. For the random effect model, we use restricted maximum likelihood to estimate sigma squared beta. And thus, intuitively, it's more similar to how regression to the mean is selecting the amount of shrinkage to apply. It's very different from using cross-validation to select the amount of shrinkage in the form of lambda. But this random effect model will give us an estimate for the true strikeout probability for each batter, which Eli is going to refer to as the random effect model when he discusses the results of applying these methods to data from the 2015 Major League Baseball regular season next.
So as Scott said, I'm going to be talking about the application of these theories that he's built up to the 2015 season. And we will start with applying regression to the mean. So for each of the 9 components that Scott laid out and each batter, we're going to use the first 200 plate appearances of the season to predict the second 200 plate appearances of the season. And the first step is to find the variance in true talent for each of these components. Now, if you look at that left column in this table, you'll see that there's a wide range of variances in true talent. Taking strikeouts, the highest variance in true talent, the intuitive understanding is that the ability of players who are best at avoiding strikeouts as batters is much better than those who are the worst. Taking hit by pitches, by contrast, as one of the lowest variances in true talent, those players who are best at getting hit by pitches are not that much better than those who are the worst. Now looking at the other 2 columns of this table, we found the error in using these 2 different models to predict from the first 200 plate appearances the result in the second 200. The 2 columns are naive and regressed. In the naive estimator, what we do is we assume that the performance in the first 200 continues unchanged into the second 200. Whereas with the regressed estimator, we apply regression to the mean in order to make our prediction. The takeaway from this table is that if you look across each row in the table, the error is decreased when we use regression to the mean. This shows that regression to the mean is a helpful tool in predicting batter outcomes. And what we did from here is we applied regression to the mean to find an estimate of wOBA. For each of the wOBA components, we applied regression to the mean, fed the outcomes into the wOBA formula using the wOBA weights, and used this as an estimate of true talent for each batter. And these are our results. So in this graph, along the x-axis, we have observed wOBA, and along the y-axis is the estimated wOBA using the methodology I just described. Each dot here is a single player, where the orange dots represent players with less than 50 plate appearances, and the blue dots are 50 or more plate appearance players. The green line is the 0-1 line, and the dashed black line is a horizontal line at the average wOBA across the league. So the takeaways from this graph, first looking at the orange dots, what we see is that these players who had fewer plate appearances are close to that dashed black line, which is to say that they're regressed harder to the mean because there's less evidence that they're any different from a league average player. By contrast, the blue players, those with more plate appearances, form a cloud that's closer to that 0-1 line, but still less slope than 1 because of the regression to the mean that's applied. If you look at the players on the far right, those with the highest observed wOBAs, and compare that to their estimated wOBA, this reflects our understanding intuitively that the very best seasons that we see are the product of players who are very talented but also benefit from luck in those phenomenal seasons. So taking a look at, or thinking about the methodology, you might think that and going with that strand of thinking about luck, you might think that the players who have the most extreme values on singles, doubles, triples, the batted ball types, would have those regressed, and in that sense we're taking into account BABIP through this methodology, and that's exactly what we see. In this graph, along the x-axis we have observed BABIP, and along the y-axis we have projected increase in wOBA. And the way that y-axis works is it's just the estimated wOBA that I described minus the observed wOBA. And what we see in this graph is a negative relationship. That is to say, those players with the highest BABIPs have a projected decrease going forward, and vice versa. Those with the lowest BABIPs are projected to increase in offensive performance. So taking the conclusions from this section on regression to the mean, what we want you to take away is that regression to the mean is a very valuable tool in projecting performance, and it's particularly valuable in accounting for sample size. Through applying regression to the mean, we no longer just have to think about samples as either too small or large enough to draw conclusions, but instead we can quantitatively assess the projections that we're able to make based on the observed data by applying regression to the mean, because we're able to account for the continuum of sample sizes rather than a binary of too small or large enough. Now I'll go into comparing each of the estimators that Scott described. Our framework here is to split each of the plate appearances from the 2015 Major League season into two sets, a training set and a test set. As review, there are 4 estimators that we used, and they are the naive estimator of assuming constant performance, the regressed estimator using regression to the mean, the ridge estimator, that's the basis for true wOBA, and the random effects model. The takeaway from this table is that if you look across each of the rows, and the numbers here give the error in the estimation, if you look across each of the rows, the regressed, ridge, and random effects models have virtually equivalent error. That is to say, these estimators are basically the same. And the way that we can see this in practice is we applied it to single rates. So in this graph right here, we compare the estimator using the regressed estimator and the ridge estimator, compare these estimates, and we see that they're virtually the same. Now I'll get into validating true wOBA. Again, we had a framework of building a test set and a training set from the 2015 season. Only this time, rather than randomly splitting up the plate appearances, we made these test and training sets characteristically different. One of them had many more plate appearances with same-handedness. The other one had many more plate appearances with opposite-handedness. The reason we did this is because true wOBA shines in its ability to distinguish these different scenarios, these characteristically different scenarios, as Scott described. And when you look down at the table in the bottom, what you see is that the error is least using the true wOBA estimator, but not statistically significantly different from the mixed model. And both of these outperform the regression to the mean based estimator by a statistically significant amount, and of course, outperform the naive estimator. Now I'll get into exactly what the results from true wOBA are. In this section, I'll be discussing the values of true wOBA for each player in a context-neutral environment. That is, if they were placed into a league average stadium against league average opponents. And that, of course, is something that we're able to do through the model that Scott described as true wOBA. So in this first graph, what we have is similar to graphs that we've seen before. We have observed wOBA along the x-axis and true wOBA along the y-axis. Once again, the players in orange, those with fewer plate appearances, are closer to that dashed black line because there's less evidence that they're any different from a league average player. And once again, we have this similar cloud of blue players closer to that green 0-1 line and a little more shallow than that line. Now turning to pitchers with true wOBA, we can also estimate the quality of each pitcher, and that's what we have here. It's a very similar graph. The difference here is that the slope of that blue cloud is more shallow, and there's a reason for this. The pitchers have less control over outcomes. There's more variance in exactly what those outcomes will be. What that leads to, in terms of this graph, is the shallower slope because it takes more evidence to show that a pitcher is as good as the observed performance. Because it takes more evidence, and this is a single season of data, there's more regression to the mean than there is with, there's more shrinkage, I should say, with pitchers than there is with batters, and we get this more shallow relationship in this graph. Now I'm going to get into exactly who performs best and worst under this true wOBA estimator. So for batters, top 5 and bottom 5 batters by true wOBA. In the top 5 are many of the names you'd expect: Bryce Harper, Mike Trout, Jose Bautista, and on the bottom 5, vice versa. Again, I should emphasize that this is these players in a context-neutral environment. Turning to pitchers, it's once again, the top 5 are some of the best pitchers, 4 players who are in the Cy Young race, Wade Davis, who had a phenomenal season as a reliever for the Royals, and vice versa with the bottom 5. So before moving on to the next slide, I'm going to explain what you'll see so you can understand how to interpret it. So I'll be, again, showing the top 5 and bottom 5 players, but instead I'll be showing the difference between true wOBA and observed wOBA. That is to say, what we expect them to perform as, or the difference between what we observe and what we would expect if they were placed into that context-neutral environment once again. So why might we see a difference between the true wOBA estimate and the observed performance? Well, there are 3 reasons. One is that true wOBA is able to account for sample size. 2 is that the players are placed into a context-neutral environment, and that has a large impact in terms of park effects. And third is that we are able to account for what are considered luck factors such as BABIP or other peripherals. So turning to batters. Here we have the top 5 and bottom 5 players, and this is with a minimum of 500 plate appearances. So taking out a couple of those examples, looking at small sample size, David Peralta is projected to drop off the most, and this makes sense because he's snuck in just right above that 500 plate appearance threshold. Thinking about park effects, we see Nolan Arenado and Charlie Blackman here, and that's because they were projected to drop off if they were placed into a context-neutral environment where they aren't taking half of their plate appearances at Coors Field. Now I'll show something very similar for pitchers. Here, once again, we see the effect of a smaller sample size with Jerome Williams, who's projected to perform much better going forward if you were in a context-neutral environment, because he, once again, was just over 500 batters faced. And then, once again, we have 2 Colorado pitchers who are projected to perform the best if they were placed into that context-neutral environment that true wOBA is able to account for, and that's because, once again, they're taken out of that Coors Field environment. So, in conclusion, we want to emphasize that the focus of this presentation is not to introduce a new batting statistic. Instead, we have these 3 contributions. First, we want to remind that regression to the mean is a very valuable tool, and especially in that it allows us to not just think of samples as too small or large enough, but it allows us to quantitatively assess what we're able to discern from the data that we observe. Second, Scott explained the relationship between regularized linear models, such as the one that goes into true wOBA, and regression to the mean. And third, we compared regularized linear models with linear mixed effects models. So that wraps up our presentation. Thank you for listening, and we'd be happy to take any questions. Well, so the question is asking about Bryce Harper. He appeared in the list as somebody who's expected to drop off in performance. So I think that goes back to our intuitive understanding that the very best seasons, Bryce Harper had a phenomenal season, is compounded by both, here he is, compounded by both being a fantastic player and also benefiting from some amount of luck. Because, the very best seasons, there are a bunch of players who are very good, but the very best seasons in an individual sense require both of those to beat out everybody else. So I think that at least intuitively explains his presence here.
Can you go back to your model, the L1 and the L2 norms?
Do you want to do this?
Is it this
Yeah,
model?
that one. Yeah, so you're actually, I think the one right before it. But you're finding that
This one right here?
I don't know if it's backwards or forwards, but you're finding that the L1 norm and the L2 norm really didn't matter. Is that more a function of the fact that your input variables here are basically only monotonic positive? I mean, that you don't have any variables that do swing negative, so it's not particularly surprising that the L1 and the L2 norms here gave you that, exact same kind of prediction.
So I apologize, I might have miscommunicated about this. We actually don't apply any L1 regularization. It's all L2 regularization.
Oh, sorry. I meant I guess this whether you were doing squared on your weights or you were just doing absolute values.
Yeah. So in the logistic regression, our loss function is the binomial log likelihood, whereas in the linear regression, our loss function is the squared error. and we got really similar results.
Right.
Because this transformation is in the response space rather than the covariate space, I don't think it's because the covariates are binary that the results are so similar. I think the reason that the results are, if you look at a comparison of the results right here, you see that the biggest differences happen for the highest probabilities and the lowest probabilities. And the reason for this is because with the linear regression, you're doing your shrinkage in the probability space. Whereas in the logistic regression, your shrinkage is being done in a transformation of the probability space. And I think that accounts for the difference between these two methods. Excellent question. Well, thanks everybody for your attention. You can find our contact information here. We've posted all code, slides, and the paper at that GitHub address, and you can find out more about our Sports Analytics Club at Stanford at the URL at the bottom. Thanks, guys.